Hello and welcome to our second lesson in Chapter 3, Part 3. Today we're going to be reviewing inverse functions. What are they? How do you find them? How do you graph them? And then we're going to be talking about something called one-to-one functions. And basically what that tells us is if we know some information about the original function f, we can determine if an inverse will actually be a function or not. So a few reminders. A relation is a function if for every x value there is only one y value. So for every input, there's only one output. In grade 10, you learned about the vertical line test, which was if you have a graph and you draw a vertical line and it only crosses once, it only crosses your graph once, then you have a function. So this has to be true for every point. So you can't be picky and say, oh, I'm going to draw it here because it's only going to cross once. No, any vertical line that is possible for you to draw would have to be able to only cross the graph once or no times. If it's going to intersect the graph more than once, you do not have a function. So function notation was instead of writing y equals, we're writing f of x equals. And an inverse function, we would use f with this little -1 here if our inverse was a function. So we can only use this notation if the inverse is also a function. In order to determine the inverse of a function, we would interchange x and y and then solve for y. If we had the graph of an original function, the inverse would be essentially all the coordinates of the points swapped. So all of our x, y values, the values would be swapped. If we look at this on a picture, on a grid, what that would look like is a reflection across the line y equals x. So let's try a question just as a refresher here for inverse functions. So if we have this function, f of x equals 2x plus 4, what does this look like if we want to sketch the function? So this would be a straight line with a y-intercept of 4, okay, and a slope of 2. So rise over run is 2 over 1, up 2 over 1. Okay, that would be our original function. So again, if we look at this, anywhere we draw a vertical line, that vertical line would cross our graph only once, which makes this a function. And also it's written in function notation, which we wouldn't be able to do if it was not a function. If I want to sketch the inverse on the same grid, I would take all the coordinates of the points I have and switch them. So for example, I have a point at 0, 4. So my new point would be at 4, 0. So my y-intercept becomes an x-intercept. I also have a slope of 2 here. On my inverse, my slope would be 1/2. Okay. So if I wanted to find the actual inverse, what I would do is instead of having y equals 2x plus 4, I would have x equals 2y plus 4. And I would solve this for y. So I'd subtract 4 sides. I would divide by 2. Now I like to graph in y equals mx plus b form. So I would split this into 1/2 x minus 4 over 2 equals y, or 1/2 x. Oh, that's messy. Let's fix that. Minus 2 equals y. So this would be my inverse here. Okay. So if I graph this, I have my original graph. I can just switch all the points if I want. So all my x and y values could switch. But now I also know that this is a linear function as well, with a slope of 1/2 and a y-intercept of -2. And that matches up with the point I previously put on. And oh, that didn't go through very nicely. this would be y equals 1/2 x minus 2. Okay. Now, if I draw the line y equals x, you can see that this looks like it's been reflected across this line, okay? So because this is an inverse, we can also write this as f with a little -1 of x equals 1/2 x minus 2 since our function, meaning all of my points, no matter where I draw a vertical line, I will only cross the graph once. Okay. We also have a point that's on both graphs here. This would be your invariant point. And this is because x equals y, it's on both graphs. So this should be a review for you. You did this in Math 12. Okay? So your inverse, you can only write it in function notation if it's also a function. And right now we would need to graph that or be solving for a very familiar function. So if I get something like square root or a up and down parabola, but if I get a sideways parabola, I know that that's not a function. So if you get a function or an equation that you are familiar with, you'll be able to tell if it's a function or not. Or if it's a graph, you can easily tell by looking at the graph. Now, there's another way that we can tell if the inverse will be a function, and that is to be looking for if the original function is 1-to-1. Okay, so this is a new definition for you. A function is considered 1-to-1 if for every y value there is only one x value. So for every output, there's only one input. And instead of a vertical line test, we would do a horizontal line test. So a function is 1-to-1 if and only if no horizontal line will intersect the graph more than once. And if a function is 1-to-1, then its inverse is also a function. And that's because if you were to reflect that graph across y equals x, when you get the inverse graph, the horizontal line test become a vertical line test. And so you'd be going from looking for every y value has one x value to every x value has one y value. So everywhere we see the word y value and x value, those switch for our inverses. So if the original function is 1-to-1, then the inverse is also a function. If a function has an inverse, we say it is invertible. So if I want to know if something is 1-to-1, I can do a horizontal line test. Okay. So this first graph would not be 1-to-1 because if I draw a horizontal line, there are many places where we have multiple x values or we cross our graph multiple times. So this is not 1-to-1. It fails the horizontal line test and it has two x values for one y value in multiple places. Okay. The other graph, if I draw a horizontal line, no matter where I draw it, I'm only crossing my graph once. So this is, yes, this is 1-to-1. Okay. And if I think about this, I wouldn't draw this on your notes, but if I think about this, the inverse of this absolute value one, the inverse would look something like this. And so if we draw a vertical line, we can see that vertical line would cross more than once. This other one, if I draw, it would look something like, see, like this. And so same thing, I can see if I were to draw vertical lines, they would only cross once. Okay, so you can see the relationship between 1-to-1 and inverses being functions. Now, you might be saying, okay, so what does this have to do with calculus? Well, we're going to use calculus to determine whether a function is 1-to-1 so that we don't have to graph all of these things, because a lot of this that we're doing right now is relying on the graphs, right? We're relying on the graph to draw a vertical line, to draw a horizontal line. So if I have a function, I've got a couple types of functions I might see. I might have a function that is always increasing as I go left to right, or always decreasing. Or I might have a function that at some point it starts increasing, and then at some point it turns back around and heads the other way. And then it might head back up this direction some. Or I might just turn around once, right? These are all types of functions. Okay. So a function is one-to-one if it is always increasing or always decreasing. So always increasing would mean no matter where I draw a tangent line, the slopes of all those tangent lines are positive. So f prime is bigger than 0 for all x in our domain. If it's always decreasing, your f prime would be less than 0 for all x in your domain. Okay. So if I take a look at all these functions, these are all f. If I wanted to draw tangent lines to all these functions, this one, tangent lines that look like this. This guy would have tangent lines that look like this. This one. And you could draw many more than this. I'm just showing some examples. So you'll notice for the first graph, this graph is always increasing. All of our tangent lines would have positive slopes, which means f prime would be bigger than 0. Positive slope means f prime is bigger than 0. The next graph, you would have all negative slopes, meaning f prime is less than 0. These two, you have a mix of positive and negative slopes and slopes where there's 0. So these graphs, f has maximums or minimums, which means f prime is equal to 0. Those are the horizontal tangent lines somewhere. Now, if I think of these graphs f, if I were to invert these or reflect these across the line y equals x, you would notice the first two would also be functions. This second one here, if you were to reflect this, it would look something like this. That would not be a function. If I reflect the parabola, it looks like this. That is not a function. Okay, so you have calculus here that can help you figure out if an f is one-to-one, and therefore if its inverse would be a function. So if you are always increasing or always decreasing, meaning f prime is bigger than 0 or less than 0 for every value, your function is one-to-one. If your function has a maximum or minimum somewhere, it can't be one-to-one, because if you turn that sideways, you're going to have an overlapping portion where your vertical line test would fail. So a question might say, is this function one-to-one, or does this function have an inverse that is also a function? You haven't been given a graph. It might be something that's not easy to graph or something that's not easy to actually find the inverse. That's where using calculus to determine if something is one-to-one would be helpful. A couple other questions here that we'll try. So if you have f as a one-to-one function with a domain of A and a range of B, first we know that the inverse is also a function, and we know from grade 12 that our domains and range would be swapped. So if our function is one-to-one, has a domain A and range B, our inverse would be a function with a domain of B and a range of A. We also then know that if our original point is f of x equals y, if our original point is xy, then on our inverse, our point would be yx. Right? We know that that's true. So we've got a question here. So it's telling us on f of x, we have the points 1, 2, 2, 3, and 3, 1. Okay, that's what's been given to us right here. We are being asked to find the inverse of 1, the inverse of 2, and the inverse of 3. So we know on our inverse, our points would be 2, 1, 3, 2, and 1, 3. Okay. So that means that f of inverse of 1 would be 3. F inverse of 2 would be 1. And F inverse of 3, 2. Okay. So these are all points x, y. These are all the flipped versions y, x. And this was asking us for the inverse of now the inputs are y's. I find it helpful to make a little table or a list. A property of inverse functions, if you have the inverse function of f, it will equal x. And if you have the function of the inverse of x, that will also equal x. But notice how this is using an inverse function. If the inverse is not a function, this won't work. Okay, so notice how it says inverse functions. Your inverse must be a function for these to be true. So we're going to show that that works for one specific example here. So if you have f of x equals root x minus 2, we want to show that if you plug the inverse f negative 1 of x into f, notice how f is the outside function. So if I want to plug inverse into f, it will equal x. That's what this is telling me. We want to show that this works. So in order to do that, we would need to know what the inverse function is, right? And we would need to know that it is an actual function. So if I want to find the inverse, I would have x equals root y minus 2 plus 1, or x minus 1 equals root y minus 2, or x minus 1 squared minus 2, x minus 1 squared plus 2 equals y. So now that we have our inverse, we know this is a function, this is a parabola, right? So this is a function. Oh. So for every input, we only have one matching output. Any x value we put in will only result in one y value. So this is a function, which means that our inverse function, if I write this in the proper notation, is x minus 1 squared plus 2. So we are being asked to find f of the inverse. So if I want to find f of inverse, my f of is root. Instead of x, I have inverse minus 2 plus 1. So what I need to do is actually plug that inverse function I found into my f. So this is going to be root, and this is going to be x minus 1 squared plus 2. That's my inverse. But then I still have minus 2 plus 1. The plus 2 minus 2's cancel out. So I end up with the square root of x minus 1 squared plus 1, which gives me x minus 1 plus 1. The square root and the squareds cancel out. And this equals x because the minus 1 and plus 1s cancel out. And so we showed that this equals x. Very fun. So the first step is we can't do this. We can't plug the inverse into f if we don't know the inverse. We found the inverse. That's a function. So we can go ahead and plug that into f. When we do that and we simplify everything, we can see that this equals x. And that is it for today.